In this video we're going to look at measuring standard electrode potentials. So we've now seen that a cell is composed of two half cells and that they are connected to each other via an external circuit and a salt bridge. And we've said that when we're looking at a cell, we need to have an idea how much of that cell's potential comes from how much reduction is occurring and how much comes from the oxidation, so that we can know which two half cells to combine to get the voltage we desire. And so we're measuring against the standard hydrogen electrode, and when we do that we measure something called the standard electrode potential. And the standard electrode potential is defined here as the EMF of the half cell compared to a standard hydrogen half cell measured at the standard conditions of 298 K, solutions having concentration 1 mole per decimeter cubed and gases having pressure 100 kilopascals. So we're measuring the voltage with the standard hydrogen half cell and then whichever thing we're trying to investigate. So let's just look at that for the cell that we introduced in the last video. Let's look at that for the copper half cell, and then let's look at it for the zinc half cell. So I want to measure how much of that 1.1 volts was due to copper. So we get given this kind of standard representation of Cu2 plus Aq slash Cu, and it's always the first thing that is going to get written first in our half equation. So Cu2 plus Aq. We're going to put our reversible arrow over here, and then we're going to say Cu solid over here. That was the thing that came after the slash, and then we can balance that equation with electrons or hydrogen ions and water if it was a more complicated half equation. So when we want to measure, if you remember back, there was a little instruction that we always put hydrogen on the left and the thing we want to measure on the right. So we're putting these two species, copper 2 plus and copper, in the right hand beaker. So because copper is a solid, we can use a copper solid electrode. And because we want a solution of Cu2 plus, we're going to use something that contains Cu2 plus. So for example, 1 mole per decimeter cubed copper nitrate solution. And that's the right hand side set up. We're going to measure it against the standard hydrogen electrode. So the standard hydrogen electrode, if you remember from the previous video, is hydrogen gas at 100 kilopascals, that's the standard pressure, but there is no metal in the hydrogen half equation. If you just remember it, if I just put it in brackets here, it was like this, H2 plus 2 electrons, so H2 gas plus, oops, not H2 gas, 2 H plus Aq, plus 2 electrons goes to hydrogen gas. There's no metal in that, there's hydrogen gas and hydrogen ions. So we're going to have a solution here containing 1 mole per decimeter cubed H plus, for example 1 mole per decimeter cubed HCl. We then got our high resistance voltmeter. And a salt bridge which contains, and I always like to use potassium nitrate, but remember it could be potassium chloride. You would need to be careful that it didn't react with either things in the beakers. So when this cell is set up like this, so it's all arranged, connected, the voltmeter reads 0.34 volts, and we see that the copper electrode is attached to the positive terminal of the voltmeter. That means that the hydrogen must be attached to the negative, and we said the voltmeter was reading 0.34 volts. And because it was more positive, because it was the positive terminal of the voltmeter, it was more positive, it gets a positive sign. And because it's the more positive, and electrons always flow to the positive electrode, they're going to flow from the platinum electrode, which remember is the negative. That's the platinum electrode of the hydrogen half cell, to the copper electrode of the copper half cell. Now, it takes an awful lot of effort to draw those beakers out every time, so we have a sort of shorthand representation of those beakers. I'm going to show you the representation and then we'll fill in the information at the top. So this little section in between these boxes is that conventional way of showing those beakers without drawing them out. So on the left hand side, what we can see is that if we start from the very left, we've got platinum, that's our electrode. The two very furthest out things on this, so the platinum here and the copper here, are the things that the voltmeter is attached to. They're the electrodes. We've then got the things that were in the left-hand beaker, hydrogen gas and hydrogen ions, and the things that are in the right-hand beaker, copper 2+ ions and copper solid, divided by a double line. That double line represents the salt bridge. A single line represents what's called a phase boundary, so a different change of state. So where platinum is a solid and hydrogen is a gas, there's a phase boundary. Where hydrogen is a gas and hydrogen ions are a solution, there's a phase boundary. Where copper ions are a solution and copper is a metal, there's a phase boundary. What I like to think about is that we're attaching like a crocodile clip to these two ends, and in this one the electrons would flow, there was flow to the positive electrode, so they would flow from this side to this side. Now that blue bit is not actually part of the diagram. The electrons are flowing towards copper from the platinum hydrogen half cell. I'm just going to remove that because that's not actually part of the diagram. Okay, so if we go back up, there are some things to think about when we draw this version of the beakers without drawing beakers. So a vertical solid line indicates a phase boundary, a change of state. Double vertical line shows the salt bridge and is in the middle. When I'm writing my representations, I always start with that. So our solid vertical line is a phase boundary, a double vertical line is the salt bridge. The species with the highest oxidation state for each half cell is written next to the salt bridge. So if we just go back to our diagram, hydrogen ions are +1, hydrogen is 0. Hydrogen ions are higher. Copper is 2+ there and 0 here. The copper 2+ is higher. What this is about is it's showing you that the order of the things, that hydrogens are being oxidized to hydrogen ions and copper 2+ are being reduced to copper metal, showing you the order. So reduced species, oxidized species, reduced species. When measuring the standard electrode potential of a half cell, the hydrogen is always shown on the left-hand side. Any other chemical cell, so that one's just like a special case, for any other cell, positive is always on the right-hand side. And that's going to be the reduction. And negative is always on the left-hand side. So as we now start to draw these beaker diagrams, we'll also draw out this conventional representation that saves us time. When you want to find the potential of any half cell, what you do is the right-hand side minus the left-hand side. And since in this one, it's hydrogen on the left, which is 0 by definition, we're going to have that the electrode potential of this cell is the right-hand side, 0.34 minus 0, which is obviously 0.34 volts. So let's have a look at the other half cell that we started to investigate, which was the Zn2+. So remember, you take the first thing written, Zn2+. You leave a little gap because you don't know where you're going to put things. And then you write the thing after the slash, zinc, and you balance the half equation. On the left-hand side, you've got the hydrogen half cell. So remember, that's 2H plus 2 electrons in equilibrium with hydrogen gas. So we want to have in this beaker hydrogen gas at 100 kilopascals, that's its standard condition. We need a platinum electrode. Now they've labelled that the arrow point says something moles per decimetre cubed H2, but we want 1 mole per decimetre cubed H plus. So to get that, we would have 0.5 mole per decimetre cubed H2SO4. We've got our salt bridge of KNO3. We've got our high resistance voltmeter. And on our right hand side we've got our zinc beaker, which has got zinc solid and 1 mole per decimetre cubed Zn, something that contains Zn2 plus, so I'm going for zinc nitrate. When you set this up, the voltmeter reads 0.76, so 0.76 volts, but the zinc is the negative, and therefore it is more negative than the hydrogen. So this ends up being the negative, and this ends up being the positive, which means that electrons would actually have to flow backwards in this circuit. So electrons always flow towards the positive. So they're going to flow from the zinc to the platinum. How would we do the conventional representation? So we'd put a double line in the middle to represent the salt bridge. You always on the left-hand side put the beaker that's on the left, in this case the hydrogen, and on the right-hand side put the beaker that is on the right-hand side, in this case the zinc. So out of the Zn2 plus and Zn, who's got the highest oxidation state? Well, it's Zn2 plus. And then Zn's got the lower oxidation state. Now those state symbols are different, so you draw a single line between them to represent the phase boundary. Then you say to yourself, can I connect a crocodile clip to a piece of zinc? If you can, you've finished that beaker. On the left-hand side, we had hydrogen ions and hydrogen. And hydrogen ions are a higher oxidation state than hydrogen, so hydrogen ions go nearest the salt bridge. Hydrogen comes further away. These have different state symbols, so a single line. Can you connect a crocodile clip to hydrogen? Well, no, you had to connect it to platinum. Can you connect the crocodile clip to that? Yep, and so you finish the conventional representation. So in the next video, what we'll do is look at a series of other half cells and how we would measure their standard electrode potentials.